In computer architecture, we sometimes take help from some very small and simple benchmark we call micro-benchmark to target some specific property of an architecture and find out what's underneath the hood in a specific CPU design. In this lecture, we're going to look at one specific micro-benchmark that's targeting the memory system. And this is what it looks like. So we loop for some large number of time in the outer loop, and in the inner loop, we loop over a vector. And we take loop over a vector using some stride, and we access an element, each element with that stride in this vector. So it's a very, very simple, it's a very simple program. Then we do this for different vector sizes, and we do this for different strides, and we measure the average access time to memory for the combination of vector size and strides. And by looking at the average access time for different vectors and strides, we are able to reverse engineer the memory system of the specific architecture we're looking at. However, in order for this to work well, we have to turn off the hardware prefetching. As you may recall, the hardware prefetcher looks at the access pattern and that we do right now, and if it's a very regular access pattern, typically, for example, strides, then the hardware prefetcher is going to outsmart us and always make sure that we're going to find whatever we're looking for in the cache. So here we assume that the hardware prefetcher has been turned off. So as I said, we're going to loop over some number of vector sizes. So a vector size 16, stride 4, we're touching every fourth element in the vector. And then for vector 16, we do stride 8, touching every eighth element, and so on. And for different vector size, as I said before. It's a simple measurement to do, and the outcome's a pretty picture. But before we look at the picture, let's look a little more about what accesses using different stride, what that implies in terms of hitting and missing in the cache. So we have a specific vector size that we are using right now, and as a first experiment, we're going to access all the elements in the vector. Then we're going to use the stride of 2 and access every other element, every fourth, every eighth, and so on, up until a stride of 16, which is equal to the vector size. Okay, and we're going to repeat this over and over again. So once we come to the end of the vector, we're going to go to the beginning of the vector. We're going to use the same stride, same vector again, over and over again, and we measure the average access time. So if you look at, and we do this for a specific cache size, and we don't know what the cache size is. So the rule of the game is to figure out what the cache size is. So for example, we could have a cache size, as in this picture, that is of a size which is twice the vector, and that the cache has been divided into cache line, where each cache line in this example is half the vector size. And so each cache line can hold up to 8 of these vector elements when we access all the elements in the cache. But we don't know this, so our goal is to try to, given that we measure the average access time in these kind of experiments, we're going to try to guess what the size of the cache is and what the size of the cache line is. As a side remark here, now in this example here, we're going to assume that the cache is a fully associative cache and it has LRU replacement. Later on, we will talk about what other kind of cache organizations, what that may imply on these kind of access patterns. Okay, so let's say now for a stride of 4 with the vector size we're using right now, we're going to ask ourselves what what we expect the average hit ratio to be for a cache of this size. And since the cache is twice as large as the vector, and more specifically, we only need to fit 2 cache lines in the cache to fit the entire vector, it's easy to convince yourself that, if we repeat these experiments many times, we're going to end up with a hit ratio which is very close to 100%. We're just going to miss the very first time we go through the vector, but after that, all the elements we're accessing are going to be in the cache all the time. And actually, for this vector size, it doesn't matter what stride we're using. If we use stride 16, well, the first time we're going to bring in that very element, and then we're going to repeat the experiment over and over again. So the second time we do the experiment, we're going to find that element in the cache, and we're going to get the hit rate. And the same for all the other strides. So varying the stride here didn't make so much sense. But what if we use vectors that are larger? So we gradually make the vectors larger and larger. And in this example, we're still using stride 4. So what would be the hit ratio if we made the vector twice as large? Well, this vector just barely still fits in the cache. So first time we go through this vector, we are going to experience 4 misses, 1 miss to each of the cache lines. But once we loop over this vector a second time and a third time and a 1000th time, we're going to find all the elements we're interested in. So even here, the hit ratio would be 100%. And actually for the size 2x size, the stride we use really doesn't matter. Regardless of stride, we're always going to find the data we're interested in the cache. So that was easy. But what if we use a vector of twice as large size? So this is twice as large as the cache we're studying. What will be the hit ratio? Well, we're going to start to go through this vector and use all the elements. And now we have right here, we have filled the cache. We keep accessing more elements, keep bringing in more cache lines. So what will happen here is the first cache lines that we brought into the cache will be replaced because we have an LRU replacement strategy and it's a fully exhaustive cache. So we're going to continue here along this line here, and we're going to replace the yellow cache line, the red cache line, green cache line, and the blue cache line. And then we start off from the beginning again. So when we come from the beginning, now the yellow cache line has been replaced and is no longer in the cache. So, and then we're going to repeat that experience over and over again. So what would be the hit ratio in this example? Well, it's very tempting to say that the hit ratio would be 0% because when we come to the beginning of this vector, the yellow cache line has been thrown out. But it's slightly, the world is slightly kinder to us than that. The first element we access in this vector, when we go through it for the second time, will still produce a miss. But the second element will be inside the cache. So why is this? What kind of locality will turn the second one access into a miss? Well, that is, of course, spatial locality. So due to spatial locality, every other access will be a cache miss and every other will be cache hit. So the hit ratio will be 50% even though the vector we're using is twice as large as the cache size. And, you know, thought experiment, what if we use a vector that was 8 times as large as the cache? What would be the hit ratio? Well, that would still be 50% because still we would, due to spatial locality, every other access to our data would hit. Okay, so now we make a new experiment. We keep the vector size 4x the original size, and we change the stride. So now we use a stride 2 instead, and we go through this vector and we try to figure out what the hit ratio would be in this example. So that's my question to you. Try to figure out what is the hit ratio for this 4x vector when we go through it with the stride 2. And the hit ratio is, as I hope you answered, 75%. Why is that? Well, because you're going to miss once and you're going to hit 3 times per cache line. So actually regardless of the vector size, if it could be 8 times or 16 times, we're always going to hit once, miss once, hit 3 times for each cache line. So the hit ratio is 75%. Okay. Based on these properties, now it's, we're almost ready to start to reverse engineer a cache based on these kind of experiments. But let's first look at how these kind of hit ratios, what effects that will have on average latency, and also what we can expect this kind of behavior to look like when we have a cache hierarchy. So first of all, let's look at the cache behavior as a function of stride. So on this axis here, we have the different strides you can have, and on this axis here, we have the hit ratio that we expect. So as we already have seen, if we have a vector that's smaller than or equal to the cache size, we expect it to be 100% hit ratio regardless of the stride. However, if we have a vector that's larger than the cache size, we expect there to be a 0% miss ratio if the strides we take are large enough. Okay, so if we take a strides in this example here of 16 and larger, then the hit ratio is 0%. And then suddenly what happens here, if we take a stride which is smaller than this magic number 16, then suddenly the hit ratio jumps up to 50% because every other access to a cache line is a miss and every other one is a hit. We make the stride half as large, and now it's suddenly 75% because now we have 1 miss and 3 hits. We make it half as large, and you guys can guess what the effect will be. 1 hit, 7 misses. 1 hit, 15 misses. Sorry, 1 miss, 7 hits, and 1 miss, 15 hits. And so the hit ratio goes up and up the smaller steps we take. So by looking at this picture, we can ask ourselves, what's the magic with the number 16 here? So here we, at stride 8, we access each cache line exactly twice, because that's what this 50% number tells us. The magic thing that happens right here at 16 is we access every cache line exactly once. At stride 32, we access every other cache line exactly once, every fourth cache line exactly once. So there is no spatial locality here that we can bank on. So looking at this, the hit ratio, it stays flat at 0%. So we can draw from looking at this picture, we can actually reverse engineer what the cache line size is of the cache. It's where this hit ratio stays at 16. Now, instead of looking at hit ratio, we can look at the average latency to data, where for the cache we're studying, we have some certain miss latency and we have some certain hit latency. And if the vector is smaller than the cache size, we will always see a latency equal to the hit latency, regardless of the stride. And when looking at a vector which is larger than the cache size, then the miss latency is going to be, the average miss latency is going to be the same. The average latency is going to be the miss latency of the cache up until we make access with a certain stride. And from there on, the average latency is going to go down in what we call the ski slope here, as the Swedes say, and eventually it's going to get closer and closer to the hit latency. And once more, looking at this picture, we can draw the conclusion that the cache line size is 16. And now looking at the cache hierarchy. Now we have two caches. One cache has the first level cache has 64 kilobyte capacity, access time 5 nanoseconds, and cache line size is 16 bytes. While the second cache should say L2 here. The L2 cache has 2 megabytes of capacity, 30 nanoseconds access time, and cache line size 64 bytes. So let's see what the average latency curve would look for this kind of cache hierarchy with two levels. If we use a vector that's smaller than or equal to 64 kilobytes, we will always see the good news. We will always have an average access time of 5 nanoseconds. If we use a vector which is larger than the L1 cache but smaller than the L2 cache, then for all these strides we will see the bad news, the miss latency here, actually the access time latency for the second level cache. But when the strides get smaller and smaller, then we will start to see the ski slope. So from this behavior, we can draw at least 3 different conclusions. One conclusion is that without knowing what cache hierarchy was inside our computer, just by looking at how the different vectors behave and how this ski slope, the shape of this ski slope, we can draw the conclusion that the cache line size for the L1 cache is 16. Okay. We can also say that we know what the size of the first level cache is, because 64 kilobytes and smaller vectors, regardless of stride, we always see the low latency. And we can say that we know what the size of the second level cache is, because we know that all vectors up to 2 megabytes have this shape, and here we assume that vectors that are larger than this have a different shape. So from that conclusion, we can say that the size of the second level cache is 2 megabytes. From this curve alone, we cannot draw the conclusion of what the cache line size is of this cache. But that we will deal with in the next picture. So here we have this kind of curve where we see latency on one axis. This is the average latency to the data. And on the x-axis, we see the stride used in this micro benchmark. So, and then we have for each vector size starting at 4 kilobytes and then increasing, we draw a different curve down here, curve that corresponds to the stride that we're using and the average access time to data that we have measured using that stride. So you see, for 4 kilobytes, we have a very simple curve. It looks like this. Just this red line that I highlighted for clarity. So the vector 4 kilobytes is down there. It's very flat. So from this, we can draw the conclusion that the first level cache is a 4 kilobyte cache, because that vector and no other vector has the shape that it's staying flat. That's very important. That wasn't that hard. Then we look at the next set of curves. So actually, these are many curves that are hiding underneath each other here. You know, it's similar, and this is from a real experiment, so it differs a little bit, you know, depending on the phase of the moon and what Murph is what kind of mood that Murph is in. But we can clearly see a ski slope going up here, and then that curve goes flat, and that is, as I said, for many vectors, it's for 8 kilobytes, and all the way up to 256 kilobyte vector, but no other vectors. Has this kind of ski slope, ends there, and then it goes flat. So from that, we can draw the conclusion that we know what the size of the second level cache is. So the size is 256 kilobytes, because that's the largest vector that you can fit, that fits in that cache, and for which this curve stays flat. We can also, by looking at the ski slope, say something about the first level cache. And due to spatial locality in the first level cache, some of these strides here, even though the vector is too large to fit in the first level cache, some of these axes will benefit from the first level cache. And the way they will benefit is from spatial locality. And you enjoy spatial locality up until the point where you hit the size of the cache line in the first level cache. So by looking at the ski slope of the L2 curve, you can determine what the cache line size is for the L1 cache. And once more, the reason you can do that is that you have an L1 cache size that we know is smaller than these green vectors, but we have a cache line size, and depending on how many times you hit the cache line before you come to the next cache line, you will experience a cache hit ratio which is higher than 0, and due to that you will experience this ski slope behavior. So here we can draw the conclusion that the cache line size is 32 bytes. Moving forward, we have the 512 kilobyte curve, and this is the shape it has. It goes up using another ski slope up to some kind of plateau here, and then it goes flat again. Okay, so this is another ski slope. It's a ski slope of the next curve, or rather the first curve that doesn't fit in L2. Okay, what can that ski slope tell us? And just to give away some of the solutions here, this plateau here corresponds to the access time to memory in this example. Okay, so what conclusion can we draw from this ski slope here? Well, this vector 5 and 12 is too large to fit in the second level cache because the size of the second level cache is 256 kilobytes. But for small strides, we experience a ski slope, and this ski slope has to do with spatial locality. Specifically so that this, if you have a stride of 64, you are most likely that you will hit in cache line somewhere twice. And sort of you miss once, hit once, because the latency difference between memory and second level cache has been cut in half. And what we are looking at here is actually the spatial locality of the cache line size for the second level cache. So looking at 128 bytes where this curve goes flat, that corresponds exactly to the cache line size of the second level cache. So now we could determine that as well. Moving to the next curve, 1 megabyte, it has the similar behavior, it goes flat and then it drops down for a bit. And then comes an interesting curve here. So the interesting curve is this 2 megabyte curve. So that the 2 megabyte curve goes up in a peak and then goes down again. So there is a new kind of ski slope here. Actually, the shape is very similar to the other ski slopes we have seen. And that ski slope actually starts already over here, even though it's so close to the blue curve that it's hard to see what's going on. So it's a ski slope that goes all the way up here, has a peak, and then drops down. So why does this ski slope go up? And this ski slope correlates to some kind of cache line size. The question is, cache line size, it's not really cache line, it's cache line-like behavior. What is going on here? And why is it hurting this curve, which is the 2 megabyte curve, and it wasn't hurting the 1 megabyte curve? What is happening here between 1 megabyte and 2 megabytes? And the answer here is that it has to do with the TLB. So the TLB reach of this architecture is 1 megabyte, which means that if you add up the size of all the pages for which you can, the TLB can contain a translation from virtual to physical addresses, the size of those pages come to exactly 1 megabyte. So we can hold the translation for the 1 megabyte vector in the TLB, but if we have a vector which is twice as large, suddenly we can't hold all the translations of the pages, the 2 megabyte pages that make up the 2 megabyte vector. So that means the reach is smaller than 2 megabytes, and it is at least as large as 1 megabyte. So that is why we're hurting the 2 megabyte vector and not the 1 megabyte vector. And why is it falling for strides larger than 16 kilobytes? So suddenly it goes down again. Okay. Well, the reason for that is that, to give away part of the answer here, we are looking at a TLB, and we know that TLBs are organized in pages. Okay. And if you make accesses with 16 kilobytes, then you miss once per page, similar to examples here, where you miss once per cache line, miss once per cache line, so you get no benefit from spatial locality. Right here, we don't benefit anything from spatial locality in the TLB. We make exactly one access to each page. Therefore, we have to, each time we access new data, we will also have to bring a TLB entry, which we use exactly once. And since the TLB reach is too small, that entry will not be there next time we access the vector. So we will always experience misses for TLB misses for each access as well. But why is it falling down here? So the reason it's falling down is that when we have a stride of 32 kilobytes, then we will access every other page. So if you look at this picture here, and we let each colored box here, each box symbolize a page in the virtual memory system. And when we have a stride, which is twice the page size, we're going to access every other page. And since we access every other page, suddenly the entries in the TLB, we have enough entries in the TLB to keep translation for every other page. We just did not have enough entries to keep translations for every page in the TLB. So we can draw lots of conclusions from this. The TLB reach is 1 megabyte. We can draw the conclusion that the page size is 16 kilobytes, because that's where we have the peak. And from that, we can calculate the number of entries in the TLB is 64, because 64 times 16 is the TLB reach, and that comes to 1 megabyte. So that's for the 2 megabyte curve. If we have the 4 megabyte curve, then we have to wait until the stride becomes 64 before we see the same positive effect that this curve falls down, because for a 4 megabyte vector, it's first when we access every fourth entry, every fourth page, that we have enough entries in the TLB so we can hold all the translation that we need, and so forth. Finally, you can see that these curves fall down here. So why is this curve falling down? Well, it's not as easy to explain why it's falling down. It has to do with a similar effect as the TLB. When you access every other page, then you don't need all the entries. But here it's a little harder to deal with this, because a cache of this size, a cache of 256 kilobytes, that cache most likely will be a physically access cache. So you have the translation between virtual to physical before you get the indexing function of this cache. So it's much harder to reason about this. But just for now, let's just leave it and say this curve is falling down somehow, and it's much harder to determine exactly the shape of this and exactly the reason why it's falling down than it is in the TLB example. Because in the TLB, as you know, it looks like a cache by itself, but it's virtually indexed, while these kind of large caches are physically indexed. So let's leave it at that for now.